Before watching this lecture, it's useful to understand the common logarithm and the laws for common logarithm. Remember, the starting point for the common logarithm is that for any positive number c, there is a unique number a such that c is equal to 10 to the a. The common logarithm of c is then defined as this unique number a. The common logarithm is the inverse of exponentiation when the base is equal to 10. The natural logarithm is the inverse of exponentiation when the base is equal to the number e, and we will investigate the natural logarithm in more details later in this lecture. But first, a few words on the logarithmic notation. The common logarithm of the number c is typically written as log c, while the natural logarithm of the number c is often written as ln c. There is, however, some variation in the notation. The alternative notation is to denote the natural logarithm of the number c by log c, and the common logarithm of c by log subscript 10 c. If you are a logarithmic beginner, I would recommend sticking with the first type of notation, using log for the common and ln for the natural. As you continue with mathematics, you will discover that the natural logarithm is way more common than the common logarithm. Actually, the common logarithm is rarely ever seen in higher mathematics. This is the reason for the second type of notation, where log means the natural logarithm and we have no use for the common one. Since the common logarithm is a little bit simpler to understand than the natural logarithm, there are some pedagogical advantages in introducing the common logarithm before the natural one. Let's continue investigating the natural logarithm. Here I have calculated the power e to the a when a is -3, -2, -1, 0, 1, 2, and 3. The natural logarithm is defined as the inverse of this operation. That is, the natural logarithm of 2.718 is 1, the natural logarithm of 7.389 is 2, the natural logarithm of 1 is 0, and so on. Let's draw two real lines where we put exponents on the lower line from -3 to 3. On the upper line, we put the power where the base is always the number e. E to the -3 is 0.05, then we have 0.135, 0.368, 1, 2.718, 7.389, and finally 20.09. The natural logarithm can be represented by the arrow going from the upper real line to the lower real line. For example, the natural logarithm of 5 must be between 1 and 2. E raised to 1.6 is equal to 4.95, which means that the natural logarithm of 5 is slightly larger than 1.6. We can find the exact value using the ln button. Calculating e to the x for this value will then give us back exactly 5. The main point is then similar to the common logarithm. Any number c greater than 0 can be written as e to the a for some unique number a. The natural logarithm of c is then equal to this number a. The natural logarithm of 0 and the natural logarithm of negative numbers is not defined, since e to the a can never become negative or 0. If you see log x in the literature, you really cannot say for sure if this is the common logarithm or the natural logarithm. You have to check on a case by case exactly how log x is defined. We have logarithmic identities and laws for the natural logarithm, which are similar to the laws for the common logarithm. First, the natural logarithm of e to the a is equal to a for all a. This is the definition of the natural logarithm. Next, e to the ln c is equal to c for all c greater than 0. To show this, write c equal to e to the a which is the same as a is equal to ln c. E to the ln c is then equal to e to the ln e to the a, which is equal to e to the a, which is equal to c. We have rules for the logarithm of products, ratios, and powers which are identical to the case of the common logarithm. That is, the natural logarithm of a product of two numbers is the sum of the natural logarithm of the numbers. To show this, write c equal to e to the a and d equal to e to the b. Then ln c times d is equal to ln e to the a multiplied by e to the b, which is equal to ln e to the a plus b, which is equal to a plus b, or ln c plus ln d. We also have ln c divided by d is equal to ln c minus ln d, and we have ln c raised to d, then we take d in front and we get d times ln c. These two rules are simple to prove, and the proof is very similar to the case when we have common logarithm.